All right, guys. You know, Today we're going to go over 12.2 triangle sides and angles. One interesting thing about teaching you guys through distance learning is that I learned about some of your sleep habits. Like, for example, I noticed someone just turned in an assignment at 3:25 a.m. I won't name no names, but you know who you are. And several of you have also turned in things at like 2 or 3 a.m. And I can only assume that you just, you lay down in bed and you say to yourself, you know what, I need to do more math. What is this thing doing here? I don't want you there. Delete? Okay, I don't even know how that got there. So, but I'm glad that you have the option to do all this math, because what would life be like if you couldn't? I mean, happier outside of that. Anyway, things I want to talk about today starting out. I said save something for today to make things interesting. So, something to talk about is data projections. I'm sure if you guys are paying attention to the news, and hopefully you are, you hear a lot about contagion rates in Florida, and you probably hear a lot of numbers thrown around, right? You probably hear, like 2 months ago, it had been remarked by Donald Trump that, we might have deaths around 100,000. And, within like a week ago, he said, more like 60,000. And you might wonder, like, well, that's 100,000 to 60,000 deaths from coronavirus. That's a huge change in projections. And, like, where are these numbers coming from? So I wanted to show you where those numbers are coming from, okay? And how, just a little thing. I don't want to make the video too long because some of you like to threaten me that if my videos are too long, you're just going to play Minecraft instead of listening to me. So I won't talk too much about it. But I think it's Washington State University or University of Washington. I forget which one. But they have statisticians there who try to figure out how, based on how many people get infected, based on how many deaths there are per day, and based on what that state has done, exactly how many people are expected to expire as a result of coronavirus. And so here you can see this is Florida right here. You can look up any of the states like Delaware, Connecticut, Colorado, or you can just see the entire United States as a whole. And you can see deaths per day are listed. And what they do here is they have mathematical models that predict how many people are going to die each day based on past projections. And over time, they replace those numbers, okay? So this part right here with all the big pinkish block right here, that's projections for the future. It's numbers we don't know. And then the thick red line is numbers we have, okay? So as they figure out the actual numbers, they replace the shaded part with these numbers. And the shaded part represents what we call a confidence interval in statistics, confidence interval. And it's a region that contains the most probable numbers that could happen, okay? Typically, we say within 95% of a parameter, a number that we think is a true estimate of what will happen, okay? So it bounces around. It's not perfect. It's not looking to be perfect, but it's looking to give us an estimate of what things could look like. So, tomorrow, April 16th is the last time it was updated. It'll be updated tomorrow. I guess they take the weekend off. There were 72 deaths in Florida from coronavirus by official figures, at least. These figures are, if you read the news, you know that there are a lot of reasons that these numbers are not perfectly accurate. There's a lot of, well, I'll just leave it at that, okay? But tomorrow, based on this number, it could be as high as around 180, and it could be as low as, it's like, 7 or something like that. So between 7 and 180. You might think 7 to 180 is such a huge number. Like, is that really worthwhile? Well, it is, right? Because it's good to know that it's almost certain it won't be like 1,000 or 10,000 people, right? Based on past historical trends. So tomorrow, we'll get values that will fit almost certainly somewhere within this region. And based on that, you can view trends, and we have what they think the projection of deaths will be like over time into June, And this is hospital resources, which isn't as interesting to you guys. There's nothing about infections on here, and the reason is if you look at any infection graphs for coronavirus, you'll see that in Florida they are linear. Well, as I talked to you about before, viruses do not spread in a linear fashion, right? They spread in an exponential fashion. So why in the world would there be linear growth of coronavirus in Florida? Well, the only reason you have linear growth is if you're only testing a set number of people each day. So in Florida and in many other parts of the United States, not just Florida, we are severely under testing people for the disease. And so let's say that you're only testing 10,000 people a day, and I'm just making that number up. Well, if you're only testing 10,000 people a day, then you can't possibly know if 100,000 people got infected, right? It's literally impossible to figure out that there are 1,000 new infections if only 10,000 people were checked. And so since our state is under testing in terms of the potential number of infections, the growth is linear because we're only testing a set number of people each day. So we can't even capture the exponential growth. So I think personally, I haven't talked to these researchers. I think personally they don't include infections because the data is highly inaccurate, right? There are some ways, and especially with the asymptomatic rates, some research has been 30, 40, 50% asymptomatic rates, so it's like really hard to figure out exactly what's going on there. I actually had a cool opportunity to work with some data scientists who are doing work on this stuff, and I might do that. I don't know if I have time for it, but it's a cool opportunity. Anyway, and they also have projected deaths, okay? So this is, April 16th, that's their last thing. Total deaths, 668 by official numbers. And, they expect that to peak, around mid-May at, 1,358-ish. It might be a couple more here, but they expect it to be done here. And some people, I think, will look at this and think, like, that's the end, and that's when it's done. But I really encourage you to look up the Spanish flu of 1918 and what happened with that pandemic. And it came in 3 waves. Because what's going to happen here, and I'm talking about this because I care about all of you surviving this and your families. What's going to happen here is it's going to be contained at some point, and the number of deaths are going to go far down. And then people will talk about reopening the economy and going back to normal. And that is in epidemiology, that's what they call the second wave, because everything goes back to normal, and there are still going to be people who are infected who go back to normal life, and they're going to be spread all throughout the country, and it's going to create a second wave of infections. And that second wave of infections, historically, my understanding is much deadlier than the first, because instead of starting out in pockets of the country and then spreading throughout, it's already all over the country, and it just expands. So, I want to tell you guys to be careful. And when people start talking about, there have been 0 deaths today, it's time to start talking about going out again, exercise caution, because it's not going to be safe, okay? And people have not done a very good job. The media does not do a very good job representing the science of these things. Anyway, so if you look at United States of America overall, you can see that the projection is about 60,000 deaths. So when Donald Trump or Dr. Fauci, the CDC director, gives numbers on projections on these things, this is where that number is coming from. It's coming from this model right here that I'm pointing at to you. okay? And, just a month ago, the number was about 100,000. So why did it change? It's worth talking about this because, my experience is the media representation of this thing is something like, well, last month you said 60 or 100,000, and this month you said 60,000. So which is it? Make up your mind. And that's not how statistical models work. Statistical models are difficult things to put together. And so there's this comic written by my favorite comic artist, Zach Weinersmith, about how statistical models for disease spread are put together and all the unknown aspects of this. And you can find this on my favorite website / blog called 538. It's a statistical blog where they analyze politics, sports, science and health, economics and culture. And I mostly read it for the politics stuff. But the fact that 538 came together with my favorite comic artist and put this out there, I just thought, well, that's fantastic. And I read the whole thing, and it's a little lengthy, but it's entertaining and extremely informative. So you can see my website up here. You can see it up here. Just type that into your web browser or your phone and give this a read. It's worth becoming educated on these things, okay? So that's all I'll say about that. That's my little piece for today. And now we're going to talk about the math, okay? But I hope, I don't know. It's my job to educate you about more than just triangles. So let's start talking about this stuff. I still have to erase this stuff from the last lecture I just stopped recording. Okay, so today is about finding triangle sides and angles. And to do this, we are going to use our wonderful SOHCAHTOA. Okay, so I'm only going to do a couple of each kind because I don't think it's very challenging. And once I do a few, it should be obvious. So step one, with any triangle, always, what's your angle of consideration? Here it's the 64-degree angle, right? That's what we're given. Now, some of you are going to say, well, what if there are two angles? What if I have this angle down here? Then it doesn't matter. You can use any angle you want and you'll get the same stuff, okay? But if you only have one angle, that's the angle that you're considering. But it never matters which angle you pick. All angles, what's the phrase? All roads lead to the same destination or something like that. All angles lead to the same trigonometric ratios. So you don't have to worry about it. And it says find the value of x. Okay, so we'll start out by labeling these sides. This is my right angle, so this is my hypotenuse. This is my angle consideration. If I go across from it, that's my opposite. And next to it is my adjacent. Always label the angle, label all three sides, and now start the problem. Okay, don't do anything until you've done all that. And now you've done that, the first thing is to ask yourself, well, what's x? X is O. So we know that whatever we want to do has to involve O. And we have so, we have ka, and we have toa. Well, ka doesn't have an O, right? It's not going to use O. It's not going to use this x value. So ka cannot help us figure out x. Instead, it's going to be so or toa. And in this situation, we don't know A. A is unlabeled. So it's not going to be toa. Instead, we do have the value h. H is 25. So I want O, and I have h. I want O, and I have h. So it's going to be so. Okay? So the way you figure out which of the three you use is by looking at which sides are which side's given to you and which side you're looking for. So that means I know I'm going to use sine is equal to, oops, I should have, that was bad deframe. Not just sine of 64, right? Because this is sine of theta. Theta is 64. Sine of 64 is equal to O over H. O is X. Over H is 25. So we want to solve for X. So to solve for X, all you have to do is multiply both of these by 25. That's very easy. What if you guys can hear the crickets? I have crickets in my house. We keep them in the bin. Big old bin of crickets. 25's cancel. So X is equal to 25 times sine of 64. How do I do that math? Well, I go to Desmos. Okay, I can close these. Can I talk to you guys about them? Whoops. That's a fun thing though. What was it? 25 times sine of 64. 25 times sine of 64. There's the answer. 22.46985,116. Piece of cake. And that's my answer. So what's the questions to tell us? Oops. Does it say round nearest tenth? Okay. So 22.5 is the answer. X equals 22.5. That's it. We're done. Not too bad, right? The only thing you really have to make sure of when you're doing these problems is this. Do you see this button here that says deg? It says when I click it, it says rad. Rad, deg. Rad, deg. Rad, deg. Do you see how this number right here is changing somehow? Rad, deg. Rad, deg. Yeah. These are short for radians and degrees, right? And maybe you remember that from geometry, maybe not. And you just want to make sure that if your number is in degrees, you keep it in degrees. And if it's in radians, it's in radians. And we'll talk more about that. The general good rule is if there's a pi in your number, that's probably expressed in radians. And there's no pi, that's in degrees. Okay? Mostly you want to use degrees. Okay? So, do I want to go over this right now? Maybe. We'll see. Let's see how I feel. Okay, so that's number one. I'll do one more of these to make sure that you're good on it, and then I'll move on to the next thing. So my angle consideration is 18 degrees, and so this is my O, my opposite. Here's my right angle, which means this over here is my hypotenuse, 34, and next to it is my adjacent, which is X. So what am I looking for? I'm looking for X, and I have H. So I'm going to use A, and I'm going to use H. What has A and H? Ca. So I'm going to use cosine. Cosine of my angle of consideration, 18 degrees, is equal to A over H, X over 34. So same idea, I multiply both sides by 34. Okay, 34's cancel. So I have X is equal to 34 times cosine of 18. So I do, oops, I have to turn off this. So I have 34 times cosine of 18. Bam, done. 32.3. It's that easy. Okay? You can click these buttons down here, cosine, sine, tangent. Do they have... looks like they don't have secant, cosecant, and cotangent. But, you know, whatever. You just flip the decimal or something. I don't know if you have problems like that. But anyway, 32.3. So that's it. X equals 32.3. That was the number, right? Lose my mind. 32.3. Okay. So yeah, that's it right there. You guys good? Yeah? Cool. Let's erase all this. And let me see. I'm not going to go over those two. I don't feel the need to go over these. Let's talk a little about this stuff. So let's talk about what is sine and cosine, okay? Sine and cosine are mathematical functions, right? Just like when I say 3 plus 1, that equals 4. How do you know that? Well, this plus sign is a mathematical operation symbol, and it's telling us to do something with these two numbers, this thing we call addition. And you know lots of other mathematical symbols too, right? Like 3 times 6. You know multiplication. 3 times 6 is 18. And you've learned what that is. And you've also learned some that look kind of weird, right? Like the square root of 9. You know what the square root of 9 is? 3. That's another mathematical operation symbol. Sine, cosine, and tangent are also mathematical operation symbols. And we'll talk a lot about that in 2 weeks. But I want you to understand a little bit. First of all, I want you to understand that sine, cosine, and tangent are mathematical operations. You take sine, cosine, and tangent of something, okay? So like I could do the sine of 10 or the sine of 20. And that's just like taking this, it's the similar idea like doing a square root of 10 or a square root of 20. It's not obviously the same answer, but it's a mathematical operation. It's doing something to this 10. It's doing something to this 20. So when I type sine of 10, okay, that's 0.1736. There's a mathematical operation that this sine is doing to 10 to give me 0.1736, okay? And sine of 20 is 0.34, 30, 0.5, 40, 0.64, 50, 0.76, 60, 0.86, 70, 0.93, 80, 0.98, 90, 1. And now watch what happens when I go up to 100. 0.987. Was that the same thing as 80? 0.984, sorry, 0.9848. 0.9848. That's weird. Why is 80 the same thing as 100? Why? Let's try another one. 10. Sine of 10 is 0.1736. What about 170? Do you see how, if I add the 7 there, the number doesn't change? Think it's broken? It's not. Sine of 10 and sine of 170 are the same thing. Why? Okay? I want you to get just a little bit of insight into what sine and cosine and tangent are doing. You will never have to figure these calculations out manually, okay? It's beyond your ability level in this math class. But having a conceptual understanding is important, and for that, we're going to look at this beautiful animation right here, okay? And what we have here is something called, and we'll talk about this in depth in 2 weeks. You do not have to have this memorized yet. I stress yet, because in 2 weeks you have to memorize this circle and its different features. But for now, I just want you to look at it and realize what we're getting out of it, okay? So the unit circle, what's special about it is that it's a circle that has a radius of 1. See, this is the center of the circle at 0, and it goes out here to 1. So radius of 1. And if this, as this radius travels around, it's going to make a triangle. Watch. So you see it's coming up here. Here's my hypotenuse of the triangle, and it comes straight down. Ignore this symbol right here. Okay, this is our triangle with the green line going down right here. Here's my triangle, and I'm pausing it real quick. Here's theta. Here's my hypotenuse, and it's coming down right here. Okay, as this hypotenuse travels around the circle, that hypotenuse stays a constant of 1, okay? And it's creating an infinite number of triangles, right? Again, looking at the green here, this green here is where the triangle ends that I'm talking about. Forget this part over here. Forget the blue line. Forget this shaded part right here. These things are not part of what I'm talking. I'm just talking about this shape right here that I'm outlining with my mouse. Okay, actually, you know, I can actually draw on this, right? Let's make it thick. I'm talking about this. I'll erase this in a sec. This is the triangle I'm talking about. Forget about the rest of that. So I want you to follow this triangle and how this triangle is changing over time, okay? So let's look at it a bit. So watch how this triangle is changing. Notice how sine is getting taller as this goes up. And notice cosine, what's happening to cosine. Cosine, this cosine line, the red line is cosine, the green line is sine. Notice how it's getting shorter? Let's stop right here, okay? I'm stopping it here. This sine, this vertical right here is 3 dots out, okay? And notice my sine is about, oops, I didn't mean to do that. Okay, let's go back just a little bit. Okay, it's about 0.954, okay? 3 blocks away, sine is about 0.954. Let's keep going. It's gonna flip over. And I'm gonna stop it when it's at 3 blocks over here. Okay. 3 blocks over on this side, what's sine? 0.955. Over here is 0.954. It's about the same number. I'm not perfect enough to stop it exactly at the right time. But notice, what I want you to notice is this. There's a triangle that's being made throughout this shape. When the triangle, when the short side of this triangle was 3 blocks long, sine was 0.95 about. And when it was about 3 blocks long over here, sine was about 0.95. Because what sine is measuring for us is the length of a triangle's side that is vertical, okay, based on the number of degrees coming from this origin right here. So I don't think I said that very well. So let me play this a little bit and freeze it to help demonstrate the idea, okay? I'm gonna pause it right here. So if I look at this triangle, and there's 2 things I want you to look at. There's the red cosine, okay? This right here is the same as this right here, right? Those are the exact same length. And this, if you look at a triangle, it's the horizontal line of the triangle. And this part right here is the vertical part of the triangle, which is sine. And this, the red part's cosine. So in other words, what sine and cosine are giving us are the horizontal and vertical components of a triangle, okay? And specifically, not just any triangle, but the unit circle triangle. So that is why sine and cosine, they are never bigger than 1. Why is that? Because the hypotenuse of this triangle is 1. And you guys know that for any given triangle, the longest side is the hypotenuse. So if this hypotenuse is 1, then the height and the length of the triangle must be less than 1. So that is why sine and cosine will always give you values less than 1. And it's why our sine value was the same between 10 degrees and 170 degrees. Why? Because at 10 degrees, we're about this far up, and at 170, we're the same height up, but we're on the opposite side. So 10 and 70 are both the 10 and 170 are both the same number of degrees off of the x-axis. Okay, so I'm going to play this a little more. So notice as this is going up, as the angle is increasing, and my green line is getting bigger, notice how my sine, this is not sine of this number, this is my sine value. Notice how my sine value keeps getting bigger and bigger and bigger, okay? And right when it hits the peak up here, I'll try and stop it to capture it. But you'll notice that sine is 1. Almost there. Pretty, oh, it's so close. Okay, so sine of 0.9999. So why is that? Because my y, if my triangle is just a vertical line, okay, or an almost vertical line, then the y component and the hypotenuse are going to be the same, right? It's super thin, so the y component and the hypotenuse is the same. Meanwhile, what's cosine? Well, if it's all vertical, oh wow, I got it perfect. Look at that. I feel very special right now. Okay, so sine is 1 because my hypotenuse is 1, and my vertical and the hypotenuse are identical. Cosine is 0 because there's no x component. There's no horizontal component. It's a straight vertical line. Notice how tangent is undefined right here. Why is that? Well, because tangent, okay, tangent is equal to sine divided by cosine. Tangent is just a ratio of sine and cosine. And what's cosine right now? Cosine of theta is 0. What happens if we divide by 0? We get undefined, right? You can't divide by 0. So that's why this is undefined right now, because we're dividing by 0. Similarly, if we go all the way back to the beginning, okay, and cosine is almost 1, because this is my triangle, quote unquote. It's just a horizontal line. It's almost all horizontal, almost no vertical. So my vertical component's very small, almost 0. And my vertical component's almost 0. And my horizontal component is almost 1, because it's almost the same as the hypotenuse. And tangent is very small because it's sine divided by cosine. Cosine is almost 1. Anything divided by 1 is itself. If this is perfectly flat, sine would be 0 because there'd be no vertical component, and cosine would be 1. So it'd be 0 divided by 1, which is 0. Okay? So I hope that time with the unit circle helps you guys understand why these sine, cosine, tangent values are the way they are. Okay, they're not just random numbers. They're not math that you can do on your own, but they're not nothing either. Okay, so let's do a little more math with these things. What if I want to know what theta is? Okay, like what if I have sine of theta equals 0.5? What do I do with that? How do I get, what if I say, what's theta? Shouldn't I be able to figure out, if I know that sine of theta is 0.5, shouldn't I be able to figure out what theta is? The answer is yes. We have mathematical operations that get rid of sine and cosine and tangent. And you're in luck, they're really simple. It's just sine, cosine, and tangent with a little -1 written next to them. Okay? And these are named inverse sine, inverse cosine, and inverse tangent. Okay? And the way you do this is you take the inverse sine of both sides to get rid of sine. So if I have sine of theta equals 0.5, I take the inverse sine of both sides, inverse sine of sine of theta equals inverse sine of 0.5. So, I should have done that different color. Hold on. let me do this again. So it's because as I'm writing, like, I don't know if that's clear. So here's inverse sine, and here's inverse sine. Okay, so when I have sine of theta and I just want theta by itself, to get rid of sine, I do inverse sine on both sides. Inverse sine of sine cancels, just like addition and subtraction cancel, just like squaring and square roots cancel, just like multiplication, division cancel. So inverse sine and sine cancel. And what I get now is theta is equal to inverse sine of 0.5. How do I do this math? You just go to Desmos. Okay. So here's, I can close this now, because we talked about it. So I do inverse sine of 0.5. And it turns out inverse sine of 0.5 is 30. Okay? Now, if you don't want to type the main like I did, if you go to func down here and you're ready for a funky time, then you just click it here. Okay, so if I do it like this, so inverse sine of 0.5 is 30. Okay? So, not too bad. So let's do this with a couple examples. Oh, let's fill this out. So if sine of theta equals x, then theta is equal to inverse sine of x. If cosine of theta equals x, then theta is equal to inverse cosine of x. If tangent of theta equals x, then theta is equal to inverse tangent of x. Okay, so pretty simple. So these ones say find the missing angle, round to the nearest tenth. So here's my angle of consideration. What are my sides? This is my opposite. This is my adjacent. So I have O, I have A, and I'm going to do TOA. So I do tangent of theta is equal to O over A. O is 8 over A, which is 14. I want to know theta, right? So I'm going to do inverse tangent on both sides to get rid of this tangent. And inverse tangent and tangent cancel. So I just have theta equals inverse tangent of 8/14. Theta is inverse tangent of 8/14. Okay? So if I type that into Desmos, whoops, inverse tangent of 8/14. Oops. And you see that's 29.7. Okay? So this is theta equals 29.7 degrees. So that's not too bad. Let's see, how many more of these do we have? 3 more. I'll do one more of these. Let's see, this is an AH problem. Okay, so I'll do. Is that where text was? Yeah. Okay. So I will. Oh, I gotta get that bar off. Go away bar. Okay. So I'll do 8, and I'll leave 9 and 10 for you guys. So if here's my angle consideration theta, right? This is my across from right angle. This is my hypotenuse. This is my opposite. And right next to it is my adjacent. So I have an A, I have an H. So this is a ca situation. So I do cosine of theta equals A over H. A and H are 38 over 40. So cosine of theta equals 38 over 40. So to solve for theta, I do inverse cosine on both sides. Inverse cosine and inverse, cosine. Inverse cosine, cosine cancel. So now I just have theta equals inverse cosine of 38 over 40. How do I do that? Just type in a calculator. Theta equals inverse cosine of 38 over 40. So I'm gonna, here's cosine inverse 30 over 40. And there's my answer, 18.19, which I'd round to 18.2. So theta equals 18.2. Okay. And last, we just got some word problems for application. I'll go through two of them. They're all kind of like the same thing over and over again. So it's not really intellectually challenging. I'll just give you one example with the vocabulary so you have some familiarity with it. Okay. So we got two terms, angle of elevation and angle of depression. And angle of elevation is really simple. It's just we start from a flat line, and the angle of elevation is the number of degrees upward. Okay. An angle of depression is the opposite. We're starting at a top line, and the angle of depression is the number of degrees downward. So note 11 says the angle of elevation from a fishing boat to the top of the lighthouse is 5 degrees. So, it's really a smart idea to draw a picture with these. Okay. So I have a fishing boat. Boop, boop, bloop, bloop, boop. Boop, 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 boop. This is like, check that. Wow. I'm really impressed with myself. Okay. Dufresne, you've done it again. And it's an angle of elevation. So I'm going to create a flat line here. I'm going to create an angle of elevation. It doesn't have to be accurate because no one cares. The angle of elevation is 5 degrees. So this is 5 degrees to a lighthouse. So here's my lighthouse. I'm actually going to watch a movie called The Lighthouse soon. I've been keeping up with my my movies over the break. Is that what a lighthouse looks like? It does today. Okay. The top lighthouse is 161 feet above sea level. I should be like that, right? It's going to the top of the lighthouse. Okay. So this is 161 feet. How far is the boat from the lighthouse? Well, so this is my angle of consideration. So that means if this is going like this is O. This is my opposite side. This is my adjacent side, and this is my hypotenuse. What do they want to know? How far is the boat from the lighthouse? So we want to know this right here, right? I want to know what's this distance right here. So I'm going to write it as, this is O and A. That's a TOA situation. That's tangent. So tangent of 5, because that's my angle, is equal to O over A, which is 161, over A, which I'll just call X. So to solve for this, X right here, I multiply both sides by X first. Okay, my X's cancel. So now I have X tangent of 5 equals 161. And now I want to get X by itself, so I divide both sides by tangent of 5. These cancel, so I just get X equals 161 over tangent of 5. So I just go to Desmos. Went over tangent of 5. And that's 1,840. Okay. So 1,840 feet. And since the word problem, it'd be great if you said something like, the boat is 1,840 feet away from the lighthouse. But I'm writing with a mouse right now, so I'm really not going to do any full sentences, okay? Fun fact, I was talking to my friend who is a developer with Bethesda, which is a video game company. Some of you guys might be familiar with. They make Fallout, Doom, and Elder Scrolls games like Skyrim and Oblivion. And I was telling him, I don't really know like how useful this trigonometry stuff is. Like, do we really? Do people really like sit around making these triangles and doing SOHCAHTOA in jobs somewhere? Because I'm struggling to justify this to my students. And he said, "Oh yeah." He said, "I use trigonometry all the time in game development." And I said, "Really? How?" And he told me that he has to program the game when it's generating objects out in space, like trees and mountains and creatures and things like that appear on the map. He has to use trigonometry to calculate their distance from the character for interactions and things. He wasn't very specific, and I was like, "Oh, that's interesting." And I talked to him yesterday, in fact, and I said, "Hey man, would you write a word problem for me using trigonometry from something you've done in your job?" He said he would. I told him his due date's Monday, so we'll see if he pulls through for me. If not, I'm sorry. But just so you know, it does get used, If any of you are interested in doing game development, engineering, of course, is a given, but also video game development, apparently, for people who do maps and things like that. Okay, angle depression, similar idea. A fire is spotted on top of a 125-foot tall fire tower. What's a fire tower? This is a tower on fire? The angle depression to the fire. Fall. Maybe it's on top of a tower fire? I don't know. I'm not going to try and figure it out. Okay. How far is the fire from the base of the tower? So, we've got a fire tower, which who knows what that is. And that's 125 feet tall. And we're looking down at stuff at a 19-degree angle. And we want to know how far is the fire from the base of the tower. So we're looking for X. How far is this fire? Here's my fire. Pretty good. Wait, hold on. It needs a little more red. Yeah. Fire. Fire. Okay. Anyway. So, what do we have? This is my angle consideration. This is A. This is O. So I have another tangent situation. I have O and A. So I just say tangent of 19 is equal to O over A. O is X. Over A is 125. Multiply both sides by 125. And so I just get X is equal to 125 times tangent of 19, right? Because these cancel. 125 times tangent of 19. Can I leave out the times? Yeah, you can leave out the times on Desmos. Don't do it though. It's bad. 43 degrees. Or 43 somethings. 43 feet? Yeah. So this is... The fire's 43 feet away from the fire tower. Which, again, what is a fire tower? Who knows? X equals... I almost said X equals fire tower. X equals 43. Okay. So that's angle depression. Angle depression means the angle's coming down. And, oh, you know what? Wow. Okay. I'm clearly tired because the angle depression should have been up here, 19. I don't think it changes anything, right? Let me think it over real quick before I'm clearly tired, putting my foot in my mouth anymore. If this is down 19 degrees, this is our new triangle, right? It still has a side of 125. And if this is still x, yeah, well, the difference is if this is 19 now, this is now O, and this is now A. So that means the fraction's flipped. Sorry, guys. So this is A now, and this is O. So it's OA 125 over X. So just in the last problem, same idea. Multiply both sides by X, divide both sides by tangent of 19. So I get X equals 125 over tangent of 19. So I'll type that in instead. Look at this. Bam. Oh, dang it. What if I do bam? Nope. Okay. No bam. Not even. As Josh Sterner says, little bam. 363. It's a little different from 43, isn't it? So 363. X equals 363 feet. Okay. And I think, does that make more sense? Yeah, that makes more sense too. Okay. So, sorry about the mistake, guys. 363, not 43. Slight difference. Okay. Have a good night, everyone.